Hello and welcome to my talk on benchmarking the utility of double event differential privacy mechanisms. This submission is about streams. That means a conceptually infinite sequence of databases. And here in an example, we record for each individual the location where, for instance, Axel is located. And we see at first he's at the park, then goes to the beach and returns finally to the park. And the sequence continues infinitely. The query we want to make private are primarily multi-dimensional account queries. As most related work, we focus on the centralized model and a special version of epsilon differential privacy named W-event differential privacy. I want to explain now why we need a special version of epsilon differential privacy, because conceptually we could simply publish each individual database with the Laplace mechanism and get some private release. The problem is that subsequent releases of streams are often highly correlated, and this boils down to the problem of sequential composition, which says you have to sum up the budget for each release database to get the final privacy guarantee. Recapitulate that streams are conceptually infinite. That means we would need an infinite amount of noise to get some privacy. The solution to this problem is W-event differential privacy, which applies a rolling window technique and changes the privacy guarantee as follows. Instead of protecting the stream entirely, we protect each rolling window of size W. This mainly is done by a change of the composition theorem, which says sum up the budget in each window of size W, and if the sum does not exceed the available budget, the guarantee holds. Now this is a starting point for this submission, because this is a very general framework and you could design a lot of mechanisms which cleverly somehow distribute the budget, and that is what happens in practice. And now as an end user, one faces the question, which of the numerous mechanisms should I actually take? Or as a researcher, what is the current state of the art or common strengths and weaknesses of existing mechanisms? And we were in that situation quite some time, and we're a bit naive and thought, well, when publishing new mechanisms, there are always empirical evaluation, which gives us some insight what is the current state of the art, what mechanisms should we take. And the result of a large-scale literature survey is, unfortunately, we cannot compare existing evaluation. So that's actually the problem we face in this, or we tackle in this submission. First, we identify requirements for empirical evaluation. So what should you actually evaluate when you propose a new mechanism? Then we develop a benchmark meeting the above requirements, and finally conduct a large-scale evaluation to reveal novel insights. The results of our survey reveal that each existing evaluation is a four-tuple of the mechanisms that are compared, the streams that are compared, the privacy requirements, which are in our case WE tuples, and finally the set of error metrics used to quantify the mechanism's utility. As I said, all existing evaluations somehow have addressed these tuples, but they highly differ in how they instance a tuple. And in the end, that boils down to the disappointing insight that actually no two evaluations are comparable. Therefore, we identify and define requirements for each of the tuple component. However, in this talk, I will not go too much into detail with all the requirements, but focus on the major novelties of our benchmark. And with respect to data streams, we first propose to separate the evaluation into one-dimensional streams and multi-dimensional streams, because the stream properties that are decisive for the mechanism utility are highly different. For multi-dimensional streams, it's all about sparsity, so a bit boring. That's why we focus in the remainder on one-dimensional streams. In addition, we face the issue that a lot of the data sets used for evaluations are either not available or highly differ in their pre-processing steps. Therefore, we propose to use a data generator that mimics frequently used streams, and you see what is common among all the streams that they feature somehow a seasonal structure. In part B of the figure here, the slide, you see a real-world stream and on the left hand side, part A, an artificial stream generated with our generator. What you can do with our generator is to specify how large the amplitude should be and how large the expected season length can be to generate different types of data sets. In addition, we propose to extend the set of error metrics that are commonly used, because most empirical evaluations so far only used abstract error metrics, something like mean absolute error or mean relative error, but only a very minor fraction of them considers real-world tasks, something like anomaly detection or forecasting. To this end, we propose to use a BLDB EA-Track paper from last year, which proposes a benchmarking toolkit for time series anomaly detection. Let's come to the results. And here are the results for the one-dimensional streams. That means real-world streams. The results for artificial streams are quite the same. What we commonly do is to have for each stream two experiments. One where you vary the W, that means the window length, and one where you vary the available amount of budget epsilon. Here we use commonly used ranges for W and epsilon, and we first found some expected results, and the expected results are that most of the mechanism actually work as supposed. So if you increase, for instance, the available budget, the error decreases proportionally. So the mechanisms really work as supposed. We also find that the amplitude is a decisive parameter, much more important than the length of the season, and it's basically based on the numbers. So you usually have much larger amplitudes when you have season lengths. So far, so good. Besides the expected results, we also had unexpected results, and most importantly, an unexpected baseline supremacy. Basically says that among the best mechanisms, that means the mechanism having the best utility, always is one of the two baselines. The baselines are sample and uniform, and they're really, really simple. Which of them performs best depends on the amplitude of the stream, but that really means in the end that they commonly outperform sophisticated mechanisms, and that raises logically some follow-up questions. One of them is, are the baseline results actually good? So right now we use error metrics like MAE, that means mean absolute error or mean relative error, and for both of them we observe this baseline supremacy. And the short answer to the question, are those baseline results actually good, is do not overinterpret those abstract error values. They differ highly, and the informative value is, I would say, limited. We go more into the details in the paper, what they actually tell you, but here we see example releases for the three streams: flu outpatients, flu death, and unemployment. And I would say in part A of the figure, the error values represent quite well how good the private releases mimic the original stream. We see, for instance, that the release of uniform is quite the same as the original true results, but the result or the release of sample actually does not feature the seasonal structure at all. Now let's move to part B of the figure, and we see that the error of uniform is smaller than it was in part A, but it really is much more different from the true query results as before. And even worse, you see that sample actually just is a horizontal line, and it has a much smaller error value. You could use the mean relative error to somehow deal with the issue here I've discussed on uniform, but we would even hide the problem, make the utility of sample better. So the key takeaway is, do not interpret too much into these abstract error values. Another follow-up question of the baseline supremacy is, why are most sophisticated mechanisms actually worse? And one of the most important reasons is that the way how they sample the data, and the sampling is data agnostic. What they do is, imagine the following. They take a very glimpse look at the data, which costs some very minor fraction of the privacy budget to decide whether they should publish a new release costing some budget or simply use a prior release which does not cost budget at all. And what they do is they optimize the error somehow locally. That means is it better for the mechanism utility right now to publish a new release or use simply the old one? And now the problem is data agnostic publishing. We know those streams have a seasonal structure. And what happens now is that those mechanisms sample quite oftenly when the new season starts and reflect minor changes in the counts quite accurately. But in combination with quite long window sizes W, this means they run out of budget early. Usually multiple seasons fit into one window W, and that means that in the end their mechanism just publishes arbitrary values, which explains why they're actually worse than than one of the baselines. Now let's move to task-specific utility. So far we considered abstract error metrics. Now we have a specific task, which is anomaly detection, and here we use the benchmarking toolkit from last year's VLDB. And what we find here is that only for very small sizes of W, the anomaly detection on private stream releases actually makes sense. So much smaller than the window size we had on the prior slide. Also, we find that the error among all mechanisms actually is fairly equal. So let's have a more detailed look at the slide. We see the average area under curve ROC score. That means a value of 0.5, you have no prediction quality, you want a value close to 1. And if you have value close to 0, you simply inverse the labels. And as we see here that for most window sizes exceeding 8, the prediction quality actually is pretty bad, and depending on the type of outlier of anomalies, even very small window sizes make a bad prediction quality. The takeaway here from this slide is that this is a clear recommendation to integrate such a task, and therefore the recommendation also is do not invent an own one, but rely, for instance, on such toolkits as we use it here. The paper concludes with takeaways for end users and researchers. For end users, we have recommendations how to select a privacy budget and suggestions for upper window sizes that actually make sense. And also we propose a kind of novel mechanism which is a mix of the two baselines, which is the first mechanism one should try. For researchers, we have also recommendation. And what helps here is that in the literature survey we reveal that every existing W-event mechanism actually implements a common mechanism framework consisting of 4 procedures. At first, it needs to decide whether it samples. If it samples, it needs to decide how much budget to spend, then do the perturbation, and possibly or optionally explore the post-processing immunity and use some filtering technique, for instance, apply some moving average filter or something like that. And for each of the procedures, we have recommendations what to do differently. Most importantly are the recommendations for the sampling component, and here we propose to approximate a trend and not only publish the last release. So we know there are seasons, so let's approximate them. Also, the recommendation is not to be data agnostic anymore, but to, for instance, to learn a private model of the stream. So how does the seasonal structure, for instance, look like? Or if there is public knowledge on the stream, for instance, in this flu example, we know in the winter there's this season starting or something like that, then use public knowledge, for instance, to decide whether a change is worth spending budget. Also, the recommendation is not to do only data-dependent sampling, but also somehow favor sampling on a regular basis. Budget allocation, we see that most common issue here for existing mechanisms is that they are kind of too optimistic. Usually those windows are quite long and they run out of budget, so be pessimistic here and avoid running out of budget. We also have recommendation for perturbation and filtering steps. They are more into level of detail here. That's why I do not want to explain them at a detailed level. All of our benchmark is available open source and can be downloaded at the website represented by the QR code here. So, hope to see you in Vancouver.